I hope everybody enjoyed their snow day. Yeah, I enjoyed it too. So the consequence of that, of course, is that we have 2 lectures worth of stuff to get through in one day, which is probably impossible, but I'll do my best. Maybe for the best. It was if you guys have read the chapters already, this is a somewhat technical series of chapters. I guess there's 2 of them. And so maybe we can keep it more to the meta-narrative there, which I think will be more fun anyways. All right, so this might bleed into next week, which is our black hole week, which I'm sure will break a lot of hearts, but this is important too. But overall today, we're going to be discussing the overwhelming majority of a stellar life cycle. And it's actually bigger than that, of course, too, because the building blocks of stars seem to come from the deaths of other stars, which is actually a really interesting take on the phenomenon. Before we get to that, though, I want to bring up a paper that I just saw published. Maybe you guys saw this headline, too. But we were talking about exoplanets in the birth of planets last time. And a series of papers came out where they were categorizing the different solar systems that we saw using this new Kepler mission, right? Because we've only been able to see exoplanets for 10, 20 years. It's all very much revolutionizing the way that we understand how solar systems are formed, which I hope that you got from the previous lectures. But, you know, they looked out, and of course, our solar system is this very nicely ordered system where you have these big, heavy, rocky, dense planets in the interior, the gassy ones are exterior. And so for most of scientific history, we were trying to explain the formation of solar systems in terms of creating this sort of a production, which is in the upper left for you guys. All right, nope, upper right, sorry. Well, it turns out that the overwhelming majority, more than 90% of solar systems that we see with this Kepler mission actually look like this down here, which is quite fascinating. So this is what they call the similar pattern, which means that the planets are all roughly the same size, and most of them, all of these systems that are called similar systems, the planets are rocky, super-Earth, Earth-like, mini-Neptunes, and rocky planets, right? So I don't have too much of a conclusion for you about that, but I think it's going to play into what we're talking about in this course in general, which is this idea that science changes day by day. This is extremely important. I was talking about it with Quentin before class. This plays a lot into concepts about freedom of discussion and getting how knowledge bases can become tyrannical if we're not careful. And I think there's no better example than astronomy of how things are on the move, and they're on the move in a way that doesn't necessarily affect our life on Earth, so we're able to entertain wild ideas more easily than we would otherwise. But oftentimes discussions can get locked down because we think we know everything. And as soon as we think we know everything, then we're in big trouble, because whatever institution it might be that claims to know everything has then at that point entered into something close to some sort of totalitarianism, some sort of tyranny, and that's never a good thing. And so let's dive into this concept. So the whole story of stars seems to me to best be approximated by something that I call cyclic metamorphosis. Now, the textbooks often refer to the lives and deaths of stars, but I don't think this is an all-encompassing way of looking at things. Certainly, there is value in looking at astronomical phenomena in terms of our own experiences, which is actually what leads me to this cyclic metamorphosis idea. But in general, there's human beings, of course, each one of us has a birth and a death, but there's something that goes beyond each one of our own lives, right? We raise the next generation, and they carry on our knowledge and our experience, and there's something that persists and transcends the individual life. And I think that we're going to find that that's the case with stars, too, because you can't make a star without having a star in the first place, which is really interesting. It's actually something of a conundrum, because you would expect that if the universe had a beginning, that is to say, if all of the objects that are in existence, all of the matter, all the material that's in existence, all of a sudden appeared one day, then we should be able to see at the edge of that, back in time, we should be able to see a place where the stars are very different than the stars that we see today, because they didn't have stars that came before them. So they shouldn't be able to have these big elements like iron, things that can't be fused in a garden variety first generation star. You know, I would say 100% of astronomers agree that our sun is at least the second generation star, probably third, maybe much, much more. And the reason for that, again, is because something as small, I hate to say as small as our sun, but it is quite small. Something as small as our sun is not capable of crushing atoms as large as irons together, or crushing things into something enormous like a plutonium or uranium. These metals require enormous pressures. In fact, the pressures they require are bigger than the biggest stars that we know about. And so today's story, in some sense, completes the cycle for us, because it's going to tell us how, through the death of a star, through its destruction, how new elements that are otherwise impossible can appear, and how we find them on Earth and so forth. And so, in some sense, it completes our story of our own planet's history as well, because, of course, the Earth is made out of very, very large elements, right? For the most part, we're made out of iron, nickel, silicon. These are huge atoms that are too big to be forged inside of a sun, right? In the typical fusion sense that we've been talking about. So I think this is this idea that something maybe there's a progress is a really valuable cosmology. It's a really valuable worldview that I think that this astronomical story embodies. And I think that's really valuable in a sense, because I think that's the bedrock of our whole Western ideal, and the civilization that we're a part of right now is this idea that you can make something better of it later, right? And so there's also this idea that things fall apart periodically too. These stars, you know, they come together and they do a thing, and then they're destroyed cataclysmically because they can no longer sustain themselves. And I think this is also a really valuable cosmology in terms of thinking about our own civilizations on Earth too, because eventually, in every civilization, some state becomes corrupted. It can no longer bear the responsibility that it is committed to, and it dissolves, and it goes through a period of cataclysmic destruction, which I think is somehow analogous to the supernova that we're going to talk about soon, which is awful. Of course, you know, states falling apart is one of the most common stories ever, but it results in the ability of the individuals to grow from that experience and make something better, right? So the cosmology that I'm going to present to you, this cyclic rebirth, is something that I think is really valuable in terms of imagining our own future, because of course we repeat ourselves. Of course, when one civilization falls apart, a new one springs up in its place. And the new one isn't entirely new. It's just sort of built upon what came before. And so the story of stars is very much the same pattern. And you know, I'm really, really holding on to the idea that this is a story, and that stories are the best way to understand reality. But what's particularly interesting about astronomy is that, unlike the Baconian idea of science that you were taught in high school, where you have an experiment and you have controls and you test things against one another, in astronomy, we can't take a star in a laboratory and control it and do something. We can't dissect it and see what's at the core of the star. We can't even see whether fusion is happening or not necessarily, right? So everything that I'm going to show you today from, you know, which is largely laid out in your textbook, but the story that we're telling is an interpretation of the observations that we can gather, right? It's a very interesting corner of science that looks into the deep past or the distant reaches of the universe and tries to come up with a story for it, it's a very different matter than being able to actually run an experiment. And so, that's something to consider. Whatever story we have today may evolve into something very different as we come up with maybe more effective, efficient ways of explaining the processes that produce the phenomena we observe. But the one that we have today is pretty decent, at least up to a point. And so I want you to just bear that in mind, that whatever processes we can come up with to explain the stars and explain this cycle is inevitably going to be updated as we move into the future. And so this is cool. Anyways, I think that this cosmology, which it really is, right? A cosmology is something which orders nature. It enforces some order on it. This cyclic cosmology is quite interesting because all of the Eastern traditions, the Eastern mythologies, which we haven't been able to really dive into in this course, probably because they're mostly hidden behind a language barrier for me, and the Western tradition's easier for me to interpret. But the Eastern traditions are very cyclic, right? There's always this idea of a rebirth of the universe. And in the West, we have this idea of progress, right? You can always make things better. This is the fundamental value of our liberal democracy. And so the merger of these two concepts, where things are getting better, but they're also repeating themselves, this sort of forward spiral, I think, is at the heart of this cosmology. And I think that's a really valuable cosmology to embrace. So anyways, this sort of sets the context for the story that I'm going to try to unfold for you right now. All right. So we took a little break to talk about planets. But before that, we were talking about protostars, and we were talking about this HR diagram, right? And as stars age, it seems like the way that we have interpreted the HR diagram, let's just refresh. The HR diagram is essentially surface temperature versus luminosity, and there's, stars cluster into different parts on this. One part they cluster into is this straight line down the middle, which we call the main sequence. And this is really where we can think of that stars begin their formal lives as stars. They start fusing hydrogen at this moment. Well, it turns out that as they age, the theory is that they become the stars that exist off of the main sequence. They become these very hot, luminous stars, which are in the upper right-hand corner. And then eventually they become some of the more luminous, cool stars, too. So we'll talk about how that works out. Things change as they move off of this sequence, and the processes that change, the elements that they begin to use as fuel are different, and the processes by which you would use up those fuel supplies give us the idea of how long it takes for these processes to occur. Now, what's kind of interesting is that you can see the time periods necessary for these planets to move down. They're crunching down. Actually, sorry, this image is actually in reverse. So these planets are moving onto the main sequence here. It happens very quickly for a protostar to happen. These are on the order of thousands of years, right? I mean, I guess some of them are tens of thousands of years. Down here we have the smaller planets seem to take longer. But the processes happen very quickly. So, now when a star actually finds itself on this on the main sequence, we call it a zero-age star. All right. Now, they only use something like 0.7% of the hydrogen that's available to them in this fusion process. So it doesn't really change the mass of the star while it's on the main sequence there. But the chemical composition in the central regions where these fusion reactions are going on does change. So the hydrogen eventually gets depleted, the helium builds up. And this, of course, this compositional change changes the luminosity, the temperature, the size, and that's how we get the stars moving eventually off of the main sequence. All right. So this table from your textbook is kind of interesting here. So how long a star hangs out on the main sequence essentially has to do with how big it is. And you can see here the stars that are really big are going to be able to crush a lot of their material into new forms and deplete their fuel much quicker than the smaller ones, which is quite interesting. I mean, these M-class stars are thought to last for as long as 200 billion years. And that's, of course, longer than the cosmologists will tell you the age of the universe, which is thought to be something like 14 billion years. So these tiny stars can last for a really, really long time. And that's an interesting fact that's going to come into play later. So we live on a planet that's on a G-type star. And this means that we've had a long time for our planet, at least assuming, the sun hasn't interfered with the development of life on Earth. If we had been around a much bigger star, we would not have had as much stable period for life to have developed on this planet. This is really important in terms of understanding why life develops in our solar system and perhaps not in other solar systems that we see. So we're looking for in addition to the range in which the planet can exist and the part of the galaxy in which life could exist, there's also the type of star. Yeah.
So I think you're about to get to this, but in the book it says that in the search, we can apply this to the search for life in other worlds by ignoring O and B type stars since their lifespans are too short to form life. But wouldn't you also argue that it's unfair to assume that given that we only have Earth life as a reference for any kind of life?
Yes, absolutely, absolutely. Yeah, so of course, the search for life, this is a difficult topic to crack open, and it's one of the more interesting and funded topics in the wheelhouse of NASA right now in terms of basic science. Obviously, people are really interested in finding life, I think primarily because we want to find places where we could live at. And so that inherently restricts our conception of life to something that looks like us. Now, can you have life that's maybe based on other molecules besides carbon? I don't know, maybe. Can you have silicon-based life? It's very chemically similar. It can articulate in a similar way to carbon. But, personally, I tend to be skeptical of that because the precursors to the life that we have on Earth are found in these molecular clouds. And a lot of the prebiotic chemistry seems to be potentially happening before the planet is even seeded with life in the first place. There's a couple of astronomers who are working on the idea of this prebiotic panspermia, where the individual elements, like the amino acids, the enzymes, basically everything you need to make a life form, those processes are not happening on the Earth. They're happening before those elements arrive at Earth, maybe on an asteroid or something like that. And that's really upending the idea that we need to understand, when we try to understand how life forms, that we should be considering Earth-like scenarios, because perhaps the conditions necessary for the evolution of Earth are actually out in outer space to begin with, which is tricky. But yeah, life could certainly be something completely different. You're right. I think your book makes a case in one of the previous chapters about, maybe it was in one of these chapters about Proxima b, was it? And considering the idea that, it's orbiting a very small star, but it's very close to the small star. And so the potential that it could be warm enough by being that close might be different. So certain things are in harmony between our planet and the sun that we orbit. And if those circumstances were different, maybe we could have a different type of star. But that's a really fascinating topic, is life happening elsewhere? And will it find us before we find it? Oops. Okay, so let's talk about leaving the main sequence, right? So when we look at that HR diagram, we do have this population of giant red stars that we see. And the question is, how do we fit them into this metamorphosis that we've been trying to describe, this evolution of stars from these big giant molecular clouds to something that looks like our star, to something that looks like a giant burning red ball, to something that is unstable and comes apart. eventually all that hydrogen is being fused, and of course we talked before about how that fusion is generating the heat and outward pressure that is able to counteract gravity. And eventually it burns that up, right? So at that point, actually, the temperature at the center is not quite big enough. It's not enough energy to actually fuse the helium. And so gravity starts to win the battle and starts to crunch the core down even tighter. Now, as that happens, more heat is generated, and the heat actually moves outside of the core, right? Heat diffuses, essentially. In fact, it was treated like a liquid for hundreds of years. And there is essentially a layer of hydrogen right outside of the core that starts to get heated up, okay? And the heat from that shrinking core puts that hydrogen over the fusion limit at some point, and that shell of hydrogen nuclei kicks into a fusion moment, kicks into the process of fusion. Of course, this heats up the outer layers, and they start to expand more and more. And so this is how we start to get a star that's changing its form, it's changing its structure, its shape, and of course, its external appearance changes as we go. Meanwhile, the helium core continues to contract, right? And this is kind of amplifying the fusion in the shell, and there's this resonance that builds up over and over again, okay? And eventually, all of this pushes outward at an extent that becomes, in some senses, cataclysmic. Now, it's not always cataclysmic. It, of course, depends on the mass, right? Depends how much material there is to begin with for these processes to happen. And there's a few different fates that seem to fall out, which we'll get to eventually, that will determine, ultimately what's going to determine your fate as a star has to do with how big you are in the first place. And, well, it's much more complicated than that. It also has to do with who you're hanging out with, who's around you, and what your environment looks like. Unfortunately, most of the discussion that we're going to have today is imagining a star in a vacuum, right? We're trying to do that test tube thing where we isolate something and examine it. So the punchline at the very end of all this, of course, is that most of the processes that we're going to talk about today are wildly oversimplified, because it turns out that a huge decision-making factor in the fate of a star has to do with its interactions with other stars nearby. And so we'll touch on that briefly. But needless to say, let's keep it to the simple example for right now. So they are generating a tremendous amount of energy from fusing the hydrogen in the shell surrounding the helium core. And this, of course, increases their luminosity. And as all this new momentum is building up, it's pushing the outward layers of the outer layers outward. So the star grows and it gets quite enormous. There's actually a picture here. This picture is comparing the sun to that of Delta Bootis, which is a giant star, and Xi Cygni, which is a supergiant. This is this is actually an adiabatic mass loss process, which is a huge word. But I think that you can think of this as something like when you take the lid off of a pot of boiling water, the steam expands and it cools down. And that's something akin to what's happening as the star is expanding. It also cools, which gives it this reddish color, right? Remember, the hot things are the blue on a flame, cool things are red. So it's decompressing, which is cooling it. This is called an adiabatic process in thermodynamics. Good trivia word. All right, so back to our HR diagram. The theory is that these stars peel off the main sequence at some point. And this is going to explain the population on the HR diagram, which is not fitting to the nice main sequence curve. And this makes, I think this is a reasonable conclusion. It seems to fit with the theory we have for the power generation of stars, and this is nice. So, okay, There's a nice red supergiant that you can check out in the night sky. I recommend that you all do it. Back to our favorite constellation, the hero, Orion. If you check out Orion's shoulder in the upper left-hand corner, you will find the supergiant Beetlejuice. And Beetlejuice has, first of all, it's enormous. If you can see on this chart here, it's actually wider than the orbit of Jupiter, which is, of course, extraordinarily far away. It's so far away from our sun that it's absolutely gets very little light. It actually radiates more light of its own heat than it gets from the sun. But still, this star has expanded to that state. And you can see Earth's orbit there for comparison. So it would have completely swallowed us had we been orbiting this thing. And this thing was so massive that it's thought that it's only something like 10 million years old, right? As opposed to our star, which is on the order of billions of years old, okay? And so we have a very different story that unfolds for stars that start out with a great deal of mass. So check out Betelgeuse when you're out there. Betelgeuse has some other interesting characteristics. It actually varies in brightness quite regularly. And that process we'll get into in a little bit, but there's a number of explanations that have been proposed. Yeah. Well, so yeah. We'll work towards that, exactly. So that's the problem, right? As these things expand and cool, they become unstable. And they give off, they start to shed their material, right? And we'll talk about that process a bit. So that's one of the things that, and of course, a giant star like this it's not sustainable. It burns through its fuel very quickly. So it moves from the early moments to the late moments of its existence very, very quickly. And so, yeah, by all theoretical accounts, it seems like Betelgeuse won't be around for that much longer. Now, it's been around for several millions of years, so maybe it will be around for a few more. It doesn't mean it's going to disappear tomorrow, but it might. And if it does go, it will be an absolutely extraordinary sight. We have, since the birth of modern astronomy, since we've had really nice telescopes, we've never actually seen a supernova in our galaxy, which is pretty mind-bending. We see them in other galaxies, and of course, there are accounts of supernova, which I haven't even explained supernova. We'll get there. Obviously, it's the endpoint of a certain kind of star. There are accounts from maybe 1,000 years ago of folks observing supernova in our own galaxy, and they're very well documented across different cultures. So we think that they happen on the order of hundreds of years, so in our galaxy. So that would be extraordinary if we were able to see that. But people aren't totally convinced that Betelgeuse, what's going on with it, honestly. In fact, when they first noticed this, there was all sorts of sci-fi explanations that were quite popularized. Everything from alien satellites getting in the way to anything else you can think of. But ultimately, in my estimation, going along with the narrative that we're telling today, it could make a lot of sense that we're just seeing layers of the star being shedded. And so that's a process we're going to talk about here in just a second. All right, so now we have stars, as opposed to moving down onto the main sequence as protostars, now they're moving off of it. So they might spend a very, very long time on the main sequence, as we said, especially the small stars. They can spend billions, maybe hundreds of billions of years on the main sequence. But eventually, they're going to evolve, right? They're going to, and I'm not sure evolve is the right word here. I like the word evolve, but it's more of a metamorphosis, like a caterpillar into a butterfly, right? It's the same entity which is changing shape and form over time. Okay, so you can look at some of the timetables here. Of course, the very luminous, very hot stars are going much quicker than the ones which are dim and small. I think that's the take-home message here. All right, so where do we go looking for these processes? Like I said, we don't have a laboratory where we can just tease apart different types of stars. So what we do is we go and look for clusters of stars that we hypothesize might have originated from the same clumps of material in the first place, right? And this is important. This is an important assumption, which could turn out to be completely wrong, but it is the one that we predicate everything that we know on after this point. Because the idea is that if they all started with the same building blocks, then there isn't too much else that could be different about them, ignoring their local circumstances and their partners and all of this. In other words, all that we're left with is the amount of material which gets included into the star in the first place. And so we like to think that the diversity that we see has to do simply with the quantity of material that's being included there. Now, of course, different stars include different types of material, right? The universe is very chunky and inhomogeneous. And so a star, a star like ours has a great deal of first, second, earlier generation material. It has heavy elements like iron and silicon, right? There's big things that are included inside of our sun, and some stars may not have scooped up some of those materials as nicely as we did. And this is actually something I kind of failed to make clear to you when we were talking about the molecular clouds. There's obviously a lot of really heavy stuff in these molecular clouds, right? There's obviously enough metal to make something that looks like an Earth, enough metal and silicon, right? Which is essentially, our planet is essentially a big chunk of metal and rock. There's obviously big, heavy things in those molecular clouds that shouldn't, I don't think thinking about them as molecular is maybe the best way of thinking about them. Heavy, heavy stuff. And actually inside of the sun, there's something like 100 times the amount of metal and rock that you would find in the Earth. So there's a great deal of these big building blocks just floating around out there waiting to get together. All right, so the two populations that we want to examine, we can loosely group all of the clusters of stars that we see in the sky into one of two bins. We call them globular clusters and open clusters. Now, globular clusters are thought to contain very old stars, whereas these open clusters and sometimes what we call associations are very young. And let's look at the differences between those. So globular clusters, they're given this name largely because they're symmetrical. They contain hundreds of thousands of stars. Let's see, over here, we're looking at a globular cluster in our own galaxy, which is Omega Centauri. It's about 16,000 light years away. And you see the brightest stars there are these red giants that have already cooked off their hydrogen in the main sequence, right, in their cores, and they're turning kind of red-orange there. Now, as you start to see, it would make sense that globular clusters are going to be some of the oldest pieces of the Milky Way. And so we're going to see these stars that have evolved, they have metamorphosed further. And there's somewhere on the order of 100 or so of these globular clusters in our galaxy. And they're actually, the interesting thing about globular clusters is that they can be found at really far distances from the center of the Milky Way, which is quite interesting. So they're kind of cast off 60,000 light years or more from the main disk. Sometimes they're outside of the plane of the Milky Way, which kind of makes sense if you think about them as having been aged very far. Now, open clusters, on the other hand, and this picture here is actually only 6,400 light years away from us, have a very different phenotype. Well, first of all, they're smaller. Sometimes the range of these can be very old. Some of them can be fairly old, older than our sun, perhaps. But they tend to be associated with the clouds in which they are formed. There tends to be a lot of material still lying around from the early days of these stars' formation. So we think that there's still star formation going on in there. And there's actually thousands of these open clusters. This is what we see mostly. So the individual stars here maybe can survive for millions, maybe billions of years, but they only stay in these kind of clusters for a very short time. They're actually drifting apart from one another. And in these tiny little clusters, the average speed can be much greater than the escape velocity that would hold them together by gravity. And so they might not remain there very long, right? Might drift out. The term evaporate from the cluster is used, although I think that's a bit of a dangerous term to throw around here. And then, of course, we have associations, which are even smaller little clusters, essentially the same idea. Associations usually have extremely low mass stars only too, so they're harder to see. There might be gazillions of them, but of course, cold things are very hard to see in space. Okay. So the clusters tend to present themselves at with different shapes on the HR diagram. So when people were modeling these type of star nurseries, they imagined that there would be something of a shape like this. And the idea here is that the high mass, high luminosity stars have already arrived on the main sequence up there, but the low mass stars are still contracting and still moving down towards the main sequence here. And this diagram, actually this theoretical one, was actually generated something like a decade or so before we actually had the ability to observe these clusters. And so as the data came in, sure enough, the outcome was quite similar to what we just showed you as the theoretical calculation, which, of course, reinforces our idea that we're on the right path with this story that we're telling. It's quite interesting. So this is an actual cluster you see here. It's, again, in the Orion Nebula. And it's a bit more scattered, but it's reassuringly similar. Okay. So as these clusters get older, their HR diagrams they're going to shift. Most massive stars are going to use up the hydrogen in their cores, and they're going to move off the main sequence and become red giants or supergiants. And then as these clusters evolve even further, the stars with low mass are going to leave and make their way to the upper right. So this cluster here is about 10 million years old, and you can see that, well, it's difficult to see, but most of the dust around the central region has dissipated. It's been incorporated or blown off by the winds of these new stars. You can see at least one red massive star there, which stands out. And so a hodgepodge of all of these different stages is occurring, depending, of course, on how much material you had in the first place. All right, so another interesting thing happens here, and this has to do with where exactly different groups peel off from the main sequence too. So we're looking here at a cluster called M41, which is like 100 million years old, pretty young. But by this time, a good number of those stars are peeling off and becoming red giants. Now, it's interesting that you don't find stars existing in a nice train off of the HR diagram there. There aren't a lot of these intermediates, right? It's almost like they go very, very quickly from being on the main sequence to being giant stars, right? This process that leads them to expand like this seems to happen very, very fast. And this makes sense because we talked about it being a feedback loop, right? Where as these processes unfold, they feed back and generate more energy, which pushes them outward further. And so it's sort of like, you guys ever have the misfortune of being in a room when somebody is trying to speak on a microphone and it's feeding back, right? It's the same process. In that case, the speaker is telling the microphone to amplify the speaker, and then the microphone's picking up the speaker, and it just reiterates itself over and over, and you get this standing resonance, which is very powerful at some point. The same thing is happening inside of the stars to some extent in terms of the momentum of the push, that power that's being generated inside of the stars from the generation of heat as a product of all these different fusion steps that we're going to go through. Here's another version. So this is after, as opposed to a couple 100 million years, this is after 4 billion years, okay? And you can see here, the older the cluster, this is an older cluster, right? The lower points on the main sequence there, are where the stars are beginning, well, lower on the main sequence, the stars are peeling off. Let me see if I can go back and show you that. I don't have a great way of going back. Oh, I do. You can see these ones are peeling off higher up, right? These ones are peeling off lower down, right? So these are older. They're lower mass stars, and this is because most of the massive stars have already peeled off that diagram and left, right? All of the more heavy ones are gone already, and so we start to put together a picture of what's happening here as these clusters age. And so many of these stars have had time to take off the main sequence that the clusters organize themselves a lot more continuously. So let's see here. Let's compare a few of them to one another. So let's see here. Okay. You know, the younger clusters, the youngest of the globular clusters in our galaxy turn out to be older than the oldest open clusters, right? And this makes sense because we're talking about having had the time for these different phenotypes to show up, these different diversities of form to show up. It turns out that all the clusters have main sequences that turn off at a luminosity that's less than the sun. And the star formation has ceased in all of these a long time ago, and they're starting to actually be replaced with red stars. So let's see if we can look at an example here. Most of what we've gone through here so far, let's just recap this for a second. So the metamorphosis we've talked about so far is that these protostars contract. They live most of their life stably with the fusion pressure, the heat pressure being balanced by gravitation. And then eventually this fails and the star moves off of the sequence and becomes a red giant. Now here's where things start to get a little bit more interesting, because at this point the stories of different masses really start to come into play in terms of what the result will be for whatever particular star it was. And so the masses are going to inform their compositions. The compositions are going to inform their fate ultimately, and then of course the presence of nearby stars, which we'll talk about very briefly. So what happens here at the end? Let's go into the details of what's going on during this red giant expansion, okay? So if you'll recall, the red giants start off with a helium core where no fusion is possible, and they have a shell of hydrogen where that heat that's residual from the contraction of the core is able to start fusion going in that outer hydrogen layer. Okay, so the core is shrinking and it's getting hotter. It's feeding that heat outward, but it still hasn't reached the point where it can fuse the leftover helium that's at the core. Now, at some point, that contraction causes the heat to be so great, right? And you can, by the way, this is another thermodynamic process you should probably be aware of. This is happening if any of you drive cars, which I assume a couple of you do at least. In an engine, the same thing is happening, right? As you compress the fuel, you ignite it, right? So this is the same thing that's happening in the core of the star. It's crunching down. Well, once it reaches an extraordinary temperature, I'm talking about 100 million degrees, well, I guess you wouldn't say that, 100 million Kelvin, some extraordinary temperature, then all of a sudden 3 of these helium atoms can fuse together and make a single carbon. And this is interesting. You might say, why wouldn't 2 of them fuse together before that? And it's because 2 of them fusing together makes an actually a really unstable beryllium that decays immediately back into something which is also going to contribute to the process. So this process, which ultimately results in a very flash ignition of the core, we call it a helium flash. The process that leads to that is called the triple alpha process as a result of that. Alpha nuclei are essentially, alpha particles are essentially helium nuclei. Very confusing double name there. Okay, so the triple alpha process is ignited at that point. Again, we have a potential feedback loop, right? As soon as the temperature is hot enough to make this triple alpha process, the extra juice, it reverberates throughout the entire helium core, which continues to rapidly heat it. Heating speeds up the nuclear reactions, which generates more heat, and you just get this amplification cycle, which just keeps going and keeps going. And it's essentially a runaway chain reaction at that point, which is, of course, pushing the star's layers outward and outward and outward. Okay. By the way, really, really massive stars also can cook helium, and it's not through this flash process. It's more of a transition thing, but they don't live very long. Okay, so we talked about the stars moving off the main sequence. Well, as soon as the helium core flashes, they actually start to drift back towards it, which is quite interesting. So they undergo something of a transformative experience here as their composition begins to change and their layered structure begins to change. So their surface temperature increases, the overall luminosity decreases, and it starts drifting back. And this is going to essentially return the star to some sort of an equilibrium between pressure and gravity. It obtains a momentary stability there, okay? Now, this lasts for a while as long as this helium is being fused into carbon and oxygen in the core, which is what you see here on this diagram, in C of that diagram, actually. Now, in D, which is on its trip back out of this, something interesting happens. The helium actually gets exhausted, and the star starts to become a giant again, and it grows in luminosity, and the temperature goes down, right? It's more of this adiabatic cooling process. Now, the star is almost out of juice completely. It's out of fuel almost, right? So it's very near the end of the line at that point. And actually, the reason it gets all squiggly is because something crazy happens, and it's very difficult to keep track of what actually undergoes in that process. But it's thought that there might be pulsations, right? And this gets us back to the Beetlejuice situation. Is Beetlejuice doing this pulsation thing? Well, lots of stars pulsate too. I believe, I don't think it was last semester, but I think in this course we've talked about variable stars. Yeah, we talked about variable stars, right? So there is some process that lends them towards pulsating on a regular basis, depending on their composition, particularly for these giant stars. Because giant stars that start off giant can actually mimic some of the processes, especially the fusion processes that are happening in these run-of-the-mill stars that are going through the end stages of their existence. All right, so at that point, the star's core begins to collapse under its own weight. And the heat released by those, the shrinking of the carbon and oxygen core is going to feed into the helium shell, which is just above the core now. And it flashes that helium at that point, and fusion begins to generate a new net flow of energy. So we can look at, this is kind of an interesting schematic of where everything's happening in these giant stars at the end of their life. So this new kind of helium fusion begins at this point in the shell. And the thing's kind of structured like an onion, which is actually quite interesting. So actually, if you were to just take this, this thing and cool it down quite a bit and maybe make it smaller, it wouldn't look too different than something like Saturn or, yeah, I think Saturn's a good example. Maybe Jupiter too, we're not sure about the core, but the core of some of our Neptune, Saturn-y worlds seems to actually have a lot of this carbon-oxygen, right? The water worlds, what is a water world? Well, it's hydrogen mixed with oxygen to some extent, right? So this layered structure actually looks quite planetary, which I think is quite tantalizing and interesting. Because, you know, if this star was to just cool off all of a sudden as opposed to explode, you might be left with something that looked like a planet. Let's see, where were we with this predicament? Okay, so previously helium came, it rescued the collapse because it was able to start fusing and lead to more heat that was able to resist the force of gravity. But after helium nuclei are exhausted, and in particularly in these low mass stars, it's difficult to come up with the temperature necessary by collapse alone to crush those heliums together. And so it reaches a point where they simply can't sustain these reactions. And so the formation of this carbon-oxygen core is essentially the endpoint for nuclear reactions in a star like our own. Yeah.
So when you say a water world has like a proportionate amount of hydrogen and oxygen, does that necessarily mean that the hydrogen and oxygen need not be bonded, or that it need not be in liquid form?
Well, very basic condensation reactions can occur to make water. So I don't know if we mentioned it, but a huge portion of these molecular clouds is water, actually. So when you cool off hydrogen and oxygen, you make water very easily. It's a condensation reaction. And so this is a little bit of a half-baked idea. I just think that it's quite interesting. I'm always looking for, well, we have huge crises in explaining planetary formation, right? And so, one actually came across a textbook when I was putting together this lecture that was old. It was, I think, from the 90s. And they had a path drawn where there's 3 different ways stars can end. One of them is a regular nova, one of them is a supernova, different types of supernova, and then another one was that the star essentially turned into a brown dwarf. It cooled off, right? Because what's really interesting is that the line between a brown dwarf and a star is quite arbitrary, right? They've actually changed the definition of what it is. Does it fuse? Can it fuse hydrogen? Okay, if it can't fuse hydrogen, it's not a star. But it fuses deuterium, which is just a heavy kind of hydrogen, right? So, and what's interesting is if you're a star that's right on the border of the amount of mass necessary to fuse hydrogen, well, it seems logical to me that you might be able to, depending on who you interact with in your local neighborhood, you might spend some time as a star and some time as a brown dwarf, depending on what material is available to you. And so it's very strange because I can't find this alternate pathway available in the modern literature, but it seemed like it was in textbooks as much as 10 years ago, and I don't know why it's been abandoned, because it seems to me like there's got to be a lot of border candidate stars that are spending time in both sides of the planet-star universe. Anyways, I just think today most astronomers consider brown dwarfs to be failed stars in that they didn't ever form a star. I think that there's a tantalizing possibility that brown dwarfs are also failed stars, literally, in that they were, and now they're not. And maybe that plays out in other ways. The thing is, look, science is inherently conservative. We can only make stories that we have confidence in about the things we can observe. It turns out that cold things are almost impossible to observe, right? So understanding what is going on in these brown dwarfs is, especially brown dwarfs that aren't tethered very closely to a sun, that we can see their shadow essentially going past. We don't know. We do think that there are certainly very well-established theorists who imagine billions of rogue brown dwarfs, essentially rogue planets out there. And to me, I feel like there's at least the tantalizing possibility that a big part of solar system formation has to do with scooping up things that are already out in the sea in the first place, right? Which I just think is, I don't think there's any evidence. There's no one that's ever seen that happening, but no one's ever seen any of this stuff happening. That's what I'm trying to get across to you right now. We have to make stories up that include what is possible, and we only are able to ascribe some very tentative level of certainty to all the stories that I'm telling you today, because they just take too long. They're too far away, and we can't reproduce these things in a laboratory. So, anyways, I think that the crumbling line between planets and stars is a really fertile ground for development in the future, and that's going to become even more relevant when I show you what an end-stage giant star looks like, because it turns out that the end stage's onion layers are almost identical to that of the Earth. Okay, so these stars swell up and they become red giants, very large radii. There's these different feedback flashes, multiple helium flashes can occur, which essentially start to fling material in the outer atmosphere away from the star. Very, very large, wide-scale, global coronal mass ejection type events, okay? So it's thought that by the time that a star like the sun reaches the point of this helium flash, it's already lost something like 25% of its mass. And it can do that all over again when it does that loop down back to the main sequence and turns around again. So it can go through this a couple of times. And it seems like these aging stars do have these shells of expanding gas as they go away. And each one of these shells, we'll look at a picture of a couple of these in a minute, seems to have something as much as 10 to 20% of the sun's mass, which is it gives a form to something that we call planetary nebula, which is what these are. Now, the word planetary nebula is another one of the biggest disasters in cosmological nomenclature, or astronomical nomenclature, right? We've come across a couple of these. You guys have probably started to get the impression that astronomers are really bad at updating their naming schemes, right? Because planetary nebula have absolutely nothing to do with planets. This is terribly confusing. I think that they were named that way because originally they looked like disks, right? And people imagined that this was other solar systems, but no, they have nothing to do with planets. In fact, we think this is actually these giant stars shedding these outer layers, as a matter of fact, and we're looking down the barrel onto it in each one of these examples. Yeah. We're working on that. We're working on that. If you have a theory of how this is able to produce vision for some giant entity, I would be very curious to hear it. They do look like eyeballs, though. Which is actually no small coincidence that humans look for eyeballs everywhere. Actually, I don't know if you guys realize it, but humans have incredible vision compared to almost every other organism on Earth. And I don't mean we can see things really far away. Of course, eagles can see things and owls, right? But what these animals are generally looking for is motion, right? And humans can see motion too, but we're one of the only mammals that has color vision, for instance, right? I mean, our vision is absolutely essential to defining what we are as human beings. So I think it's no surprise that we see eyeballs everywhere, because eyeballs are also able to tell you, unlike all of the other primates, we have these whites around the edges of our eyeballs, right? And if you look at like a gorilla or something, they have these big brown black eyes, right? Sharks, they think about other animals, predators. But our eyeballs, because of the white, we're able to see where someone's looking. And so we're able to actually pay attention to things just because someone's looking at them. That's wholly unique in the animal kingdom, which is incredible. So I don't think that it's a surprise that you see eyeballs out there in the cosmos. I think looking for where the eyes are looking is always a critical thing that's happening when you're in a social situation, whether you realize it or not. That's what eye contact is all about. Anyways. All right. What do we want to say about these things? All right, so the cool thing about this formation of these planetary nebulas, which are essentially the outer layers being shed from these giant stars, is that it begins the recycling project, right? And this is the kind of brilliant cyclic piece of this cosmology, which is absolutely essential. These elements which are getting cast off at high energies into the void are going to eventually find their way into the production of new clouds. They're going to interact at high speeds with the clouds that already exist, and they're going to result in the production of reactions and chemicals that will eventually go into a star in the future. What am I going to say about that? Okay. Now, there's a lot of elements, however, that we find in these molecular clouds, like I said at the beginning, which are much bigger than the hydrogen and helium that are getting cast off from the shells at this point, right? So the final piece in our puzzle is, where do we get these really enormous elements from? I mean, elements that are too big to even be fused in enormous stars, right? How do you make something how do you make new atoms? Well, the natural answer is you find a really pressurized situation and you stick old atoms into it and it squishes them together. Well, the most pressurized place in the entire universe that we can think of are giant stars. But giant stars even don't have the pressure necessary to fuse something like uranium together, right? Which is an enormous atom. It's so enormous that it can hardly hold itself together, right? it'll just decay. And that's, of course, how we get all sorts of nuclear hijinks. So we have to start thinking about the actual death throes of the star to look for an energetic process that's actually capable of smashing nuclei together in order to make some of these more heavy elements. Okay. Now, before we get there, though, we can think about these massive stars. This is the layered structure that I think is, yeah, this is quite interesting here. Okay. So, really, really big stars can have additional types of fusion that's going on. Not big enough to create uranium, but they can start to create some really interesting elements, like iron, like silicon, some of these bigger things that we actually find on Earth and actually we depend upon. Oxygen, neon, magnesium. It seems like iron is the end of the road, though. In order to smash two irons together, you need more pressure than the biggest star can manage, all right? Now, before I move on, though, this is really interesting. This is essentially the layered structure that the biggest stars can create. Now, I'm not saying that I can conceive of a way in which this happens exactly, but if you were to put this thing in a freezer and it just cooled off, well, it looks essentially like the Earth, right? It has an iron core, silicon, sulfur, right? You have all of the rocky things that you need to make the outer layers, the mantle, and then of course you have all of the hydrogen and oxygen necessary to make water on top of it. That's a really tantalizing revelation. So again, the stories we're going to tell you are about exploding stars, about very extraordinary events. And why are we fixated on them? Well, we're fixated on them because they're the most obvious, most visible events, right? When we look out into the night sky at distant things that are 60,000 light years away, well, we're going to see the most visible ones. Again, if something gets cold, you're not going to see it. Yes? So the massive stars can only create elements up to iron. The supernova explosion, the shockwave pressure of that is thought to be capable of synthesizing the heavier elements than that. Now, what I'm trying to rescue here, look, what I'm proposing here is pretty outrageous, and I don't expect you to believe that I'm right about this, but what I'm saying is that there's an extraordinary crisis in planetary formation science, which is that there's a number of them. We talked about them in lecture last time when we did planets. But one of the most pressing issues is that it's almost impossible to take a pebble and make a boulder out of it in a planetary disk, right? How do you get something as dense as the Earth to crush together? Where is the pressure available to crush? This is the most dense object in the solar system. It's not inside of the sun, which is bizarre, first of all, because you would think that all of the heavy stuff would end up at the center of the gravitational system. This isn't the case, and of course, there's different braking mechanisms to rescue that. There are theoretical solutions to it, which very well may prove to be accurate, but gluing together pebbles to make a boulder is an impossible physical task. I have not seen, and I'm not aware of anyone who's solved that problem convincingly. What I'm saying is that this process of a massive star already makes something that looks exactly like the Earth inside of it. Okay? Now, if some pieces of that are able to be ejected, let's say, maybe you can get planets out of that. Maybe when this thing falls apart, it gives off chunks of itself which are great little nuclei for planets in the first place. I'm just throwing it out there. It just seems like something that needs to be said. It's an elephant in the room, that's all I'm saying. There's a number of people who are working on it. Yeah, it's an idea that's out there. Actually, if I'm going to be completely fair about it, it was first proposed by a Soviet scientist named Parin back in the 1970s. And if we go really far back, actually Aristotle had this idea that planets were essentially cooled off stars. And it was cloaked in a lot of poetic language that wasn't in any way commensurate with the understanding we have of what stars are, the processes that drive them. but it's kind of an old idea. All I'm saying is that it seems possible to me. I'm not saying it is so. I'm saying it seems possible. And of course, what I was trying to impress upon you at the beginning of the lecture today is that the planetary formation science is one of the most rapidly changing sciences that we have. Our entire body of understanding of how planets formed doesn't work. It didn't work. And when we went and started seeing other planetary systems, they looked nothing like our solar system, first of all. And our whole model was built on the presence, on the appearance of our solar system. And so the planetary science is rapidly changing. If you were ever going to see something crazy, like a completely new understanding of how planets form, if you were going to see some paradigm in science change wildly, I think you would see it first in planetary science. And next, probably in any other aspect of astronomy, because, again, we only ever make scientific theories, at least we only ever publish scientific theories that can conform to observations that we see. We'll never ever include an observation that might be possible, but we can't see it. The problem with cold things is you can't see them, fundamentally. So if what I am suggesting to you is possible, it doesn't matter because we can't see it, right? And so I think that the crumbling line between brown dwarfs and M-class dwarf stars is quite fascinating, actually. I think that it would be unreasonable to suggest that they did never transition between the two when you think about all of the matter that's being exchanged. Look, at some point, one second, Quentin. At some point, that's what's fascinating about these things. There is a threshold at which the mass builds up and one atom gets added at some point and boom, it has enough mass for fusion to start, right? So there's literally one atom that separates a brown dwarf from an M-class star, right? And so the standard canon is that, well, brown dwarfs are almost stars. They didn't get that atom. But I'm saying, what if they lost that atom? What if they were M-class stars and they lost that atom and they can't fuse anymore? Well, they'd look just like a brown dwarf and you'd have no way of knowing whether it was a star in the first place and it turned into a brown dwarf or vice versa. Go ahead.
So to ask the question of like where all the heavier elements came from, I was under the understanding that like supernova typically produced gold.
Yep.
Is the fusion. Or like what about the elements that are like on the extra two bottom rows of the periodic table, such as like Einsteinium and the heaviest Lawrencium?
That's a great question. We haven't gotten to supernovas yet, and I plan to get to them. It looks like we're going to have to bleed into next week. So those elements are hypothesized to occur in the supernova shockwaves, and we'll talk about that a bit. But I don't think that's a satisfying explanation entirely, because what's tantalizing is that at least one star, which you can look up on Wikipedia, called Przybylski's star, which is PZY something. It's a Polish name. It's very difficult to spell. Przybylski's star has evidence of very short-lived radioactive elements at its surface. Okay, elements that live for 15 minutes. How do you get an element that lives for 15 minutes appearing in a star that's supposed to have been around for gazillions of years and the heavy elements are supposed to have been incorporated from previous supernova? This is a very, very tricky question to answer. And in fact, if you read the Wikipedia article about Przybylski's star, the leading explanations are like, well, aliens are dumping their garbage into it or something like that. And I'm like, maybe. But maybe there's something more akin to a different kind of fusion happening in the outer layers of these massive stars. There's a concept that NASA's just started working on called lattice-confined fusion, which I mentioned maybe the first or second week of the course. And I'm desperate to talk to somebody who's working on this. They're very hard to reach. But it seems depending on our conception of the structure of the sun, if the structure of the sun actually has some sort of lattice that's capable of compressing elements together within these onion layers, maybe you can get fusion happening in the outer portions of the stars. So what I'm saying is that while the story that we've told you so far is undoubtedly correct within some bounds, there may be extenuating circumstances which allow all of these processes to happen elsewhere as well, right? I don't think it's a matter of, well, in the future, we'll think that stars don't fuse in their core. I'm certain that we'll still believe they fuse in their core. It's just that maybe there's other fusion processes happening that we haven't totally figured out. The cool thing about lattice confinement fusion is that it can happen at very low temperatures. Now that could prove extremely practical on Earth, because the difficulty with fusion technology on Earth right now is that you're trying to control an extraordinarily hot ball of plasma, right? Now, that's harder than it seems, right? When you have something hot, it moves really fast. Its structures are very transient. You know, heat can be thought of as speed to some extent, or fastness. And so I think that the possibility of lattice confined fusion is really tantalizing. I'd like to learn more about it. Unfortunately, I think it's such a new topic that NASA's only just started to crack the lid on that process.